Time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth.
It's one small step for man, one giant leap for mankind.
Today is a day for mourning and remembering. Nancy and I are pained to the core by the tragedy of the Shuttle Challenger.
The following program may contain coarse language, adult themes, and bad attempts at humor. Listener discretion is advised.
What is President Trump's goal? What is his vision? He wants to put an American flag on Mars.
Houston, Tranquility Base here. The Eagle has landed.
I am JEFFA, Cosmic Bard over on X, and this is the Lost Wanderer podcast for January 25th, 2026, produced live from the Listening Post Studios and simulcast on KLRN Radio, coming to you from the ACS Serenade Observatory, orbiting high above the night wintry side of Earth. Earlier this month, NASA made a decision it almost never, and actually really never has had to make. An astronaut crew aboard the ISS was brought home early because of a medical issue. The mission, known as Crew 11, ended ahead of schedule, with the crew undocked from the station. It re-entered Earth's atmosphere aboard a SpaceX Crew Dragon capsule, splashed down safely, and was recovered without incident. Within days, the astronauts were back in Houston, and NASA reporting that the crew were in good condition. Now, that alone would be notable. What makes this different is that this was the first medical evacuation from the ISS in its history. It wasn't any kind of an emergency landing or a rescue mission. It was a planned, deliberate medical evacuation from orbit. And I think it's important that this distinction matters. According to NASA, the decision was made after a medical concern was identified while the crew was aboard the station. Now, the agency has not released specific details about the condition, and I hope it never does because, let's face it, we all have our medical privacy. What NASA did emphasize was that this decision was mainly precautionary. In other words, the situation did not deteriorate into a crisis. The system in place identified a risk, evaluated it, and chose to act early. Once the decision was made, the rest of the sequence unfolded exactly as designed. Once again, Crew Dragon undocked from ISS, performed a few controlled deorbit burns, and the capsule re-entered Earth's atmosphere and splashed down in the ocean, where recovery teams were already in position. Medical personnel assessed the crew immediately, and from there, the astronauts were transported onward for follow-up evaluation and recovery. NASA later confirmed that the crew had arrived safely in Houston and remained in the good health. And once again, from outside, it looked, I don't want to use the term ordinary. How about it looked uneventful? For decades, human spaceflight has been defined by moments of improvisation. Apollo 13 comes to mind. Shuttle aborts, last-minute engineering workarounds, near misses that have become legends. Crew 11 is something different. It's a demonstration of a system that no longer relies on improvisation to keep people alive. This evacuation did not require inventing new procedures. It did not require bending mission rules. It did not require accepting additional risks to protect a launch schedule. Everything that happened was already planned for. Now remember, this planning starts before a mission ever launches. Crew medical monitoring is continuous on the ISS. Thresholds for concern are defined ahead of time. Authority lines are clear. Flight surgeons can recommend ending a mission, and mission managers can act on that recommendation without negotiation nor delay. And spacecraft availability is part of this system. Crew Dragon capsules are designed not just to launch astronauts to orbit, but to bring them home on short notice if required. And recovery teams train for these off-nominal returns. Medical staff train specifically for the challenges of readapting astronauts to Earth's gravities after shortened missions. Once again, none of this that occurred other than the medical issue is accidental. This is what modern human spaceflight looks like when it's treated as an operational enterprise rather than an expedition. And I think it's worth saying clearly, this capability exists because it is funded continuously, not because it is needed occasionally. I know we all hate to see our money wasted, and there's plenty of current events in the news about how our money is wasted. But I think in this regard, it's better to not use it than to have to use it. And when we do use it, the funding and the training and the constant training was proven to be a success. Remember, around the same time Crew 11 was returning to Earth, Congress passed a roughly $24 billion NASA budget, rejecting deeper proposed cuts to the agency from President Trump and his staff. So it's kind of funny, he gets the head to help pick the head of NASA, and NASA's like, no, we want more money. And the Congress actually agreed and kind of went against some of those cuts. Now, that said, this funding decision didn't make headlines the way a launch would, but it underrates outcomes like the one we just saw. Medical evacuation from orbit requires that redundancy. Redundancy, unfortunately, requires staffing. Staffing, done right, requires proper training, and proper training requires time and money. You don't fund those things after something goes wrong. You fund them in advance, hoping you never, ever will need to use them. And in an odd way, Crew 11 shows what that investment has bought. It has bought the ability to choose caution. It has bought the ability to end a mission early without turning it into a failure. Now, granted, Crew 11 was near end anyway, but a couple weeks ahead of time. So, hey, the option to protect human life without compromising the rest of the program was appreciated. And I think this matters because human spaceflight is entering a new phase. Yes, I know it's been there for many, many years, but the ISS, we can't treat it like a novelty because commercial crew missions fly there regularly now. The expectation now is not that every mission will push boundaries, but that the missions will operate reliable and within known limits. And that shift changes how success is now measured. Success is no longer defined by how long a crew stays in orbit or how much science they complete at any cost. Success is defined by whether the system can adapt when the conditions change, and we have to hand it to it. Crew 11 and everyone associated with it adapted. We have to think of the upcoming Artemis missions. They will push crews farther from Earth. Lunar missions will extend mission durations. Future plans call for longer stays, more complex operations, and fewer immediate return options. Before any of that can happen, agencies need confidence that early exits work when they are available. And I think what has happened with Crew 11 is an important step of proving that confidence. It demonstrates that modern spaceflight is no longer built around the heroics, though we should still celebrate them as such. It is built around discipline, around knowing when to stop, and valuing the margin as much as any ambition. I think it also will reframe a little bit of how we should think about the risk associated. Admittedly, the risk in this story does not read dramatic. It didn't involve some glaring fire or some, oh my God, decompression or system failure. It involved a medical variable that fell outside of the pre-imposed acceptable limits. That kind of risk, I think, will become more common, not less, as missions get longer and crews spend more time off Earth. The fact that the system handled this without escalation should not be a footnote. It should be the headline. What it proved is that human spaceflight has matured to the point where safety decisions don't have to wait until danger has become obvious. The crew came home early. The mission ended cleanly. The system did what it was designed to do. And speaking of the system, it's kind of a quiet success that, well, in a way will be the foundation of everything else in this episode. Because NASA has rolled out the Artemis 2 rocket to the launch pad, marking a major step forward in the agency's return to the moon for the first time for you doubters and truthers in the audience. Moon program. That is not a launch announcement. It is a transition from assembly now to integration to final pre-flight testing. With the rocket now at its pad, Artemis 2 has entered the phase where systems are evaluated together as a complete vehicle rather than individual components. Artemis 2 will be the first crewed mission of NASA's Artemis program. The mission will send 4 astronauts aboard the Orion spacecraft on a multi-day flight around the moon before returning them to Earth. Once again, this mission does not include a lunar landing. NASA has been quite clear about what the Artemis 2 purpose is. The flight is designed to test crewed deep space systems in an operational environment beyond low Earth orbit. That includes life support systems, navigation, communications, propulsion, and re-entry procedures under conditions that cannot be, well, really accurately replicated closer to Earth. Now, the launch vehicle for Artemis 2 is the Space Launch System, or SLS, paired with the Orion crew capsule. This configuration builds directly on Artemis 1, which flew an uncrewed Orion spacecraft around the moon in 2022 and returned it safely to Earth. The data from Artemis 1 informed a number of changes and refinements to Artemis 2, particularly in the areas related to heat shield performance, avionics behavior, and overall mission resilience. Artemis 2 does incorporate those updates while adding the complexity of human occupants. Now, rolling the rocket to the pad began a long sequence of checks and rehearsals and everything else that goes on behind, formerly cigarette-stained rooms. NASA will conduct, of course, electrical tests, fueling procedures, countdown simulations, and communication verification while the vehicle remains in place. These steps are intended to identify possible issues early and resolve them before a launch date is set. NASA, to its credit, has emphasized that Artemis 2 is not driven by schedule pressure. They have repeatedly stated that the crewed Artemis missions will proceed only after testing objectives are met and reviewed. That approach reflects lessons learned from earlier human spaceflight programs where schedule constraints sometimes increase the risk to ill effect. ISIS missions, ISS missions allow relatively rapid return to Earth if problems arise. Lunar missions will not and do not. Transit times are going to be longer. Radiation exposures are going to be higher. And abort options are more limited onto a spacecraft with a committed trajectory around the moon. It's important to test and understand, as Artemis 2 is designed to validate how well these current systems handle those realities with very important human cargo aboard. Now, while it moves through the pre-flight testing, NASA is also outlining what sustained lunar operations will require beyond these early missions. And as we've talked about previously on former episodes, one of the most significant discussions actually well, it centers around power generation on the moon. NASA has stated that long duration lunar missions will require reliable electrical power that does not depend entirely on sunlight. Because let's remember, the moon experiences nights lasting roughly 2 Earth weeks, during which solar power is unavailable. Batteries can provide temporary storage, but they're really not sufficient for continuous operations over any amount of extended periods. Now, to address this, NASA has discussed the potential deployment of a small nuclear fission reactor on the moon by the end of the decade. Such a reactor would be designed to produce tens of kilowatts of electrical power. That level of output would support habitats, life support systems, scientific instruments, communication equipment, and other infrastructure needed for sustained operations. The proposed reactor would be significantly smaller than terrestrial nuclear power plants, and NASA has indicated that it would be launched in an inactive state and activated only after the deployment upon the lunar surface. Safety reviews and engineering assessments would be conducted before any operational use. Power availability, maybe next to water, or maybe just equally as much as water, is a limiting factor for any long duration activity on the moon. Without a continuous power source, surface operations must be constrained to just the daylight periods or rely on a very complex system of energy storage. In regions near the lunar South Pole, where NASA plans to send astronauts, sunlight angles are low and terrain features create extended shadowed areas. So, these conditions will complicate the use of any solar array configuration that they do put in place. The discussion of nuclear power also reflects how the Artemis program differs from earlier lunar missions. The Apollo missions, well, they were a short duration visit. They relied on pre-packed resources and did not attempt to establish anything resembling a long-term surface operation. But Artemis is structured around repeated missions, increasing surface time and infrastructure development over multiple years. And with this shift changes, priorities around planning will change. Power systems, communication networks, and surface logistics, well, they become more of a central consideration rather than secondary ones. And the reactor discussion is part of this broader planning process. Artemis 2 is focused on validating that humans can safely operate beyond low Earth orbit using current systems for a longer period of time. Power discussions focus on what those systems would need to support such long-term activities once crews are regularly traveling to and from the moon. Now, NASA has not committed to deploying a specific reactor at this point, nor has it announced a final architecture for lunar surface power. But the agency has made it clear that its sustained lunar operations will require solutions that go beyond short-term mission support. And if the mission successfully validates crewed deep space observation, it clears the way for subsequent Artemis missions that will involve landings, even longer stays, and expanded service activity. If issues are identified, they will be addressed before any of these steps are taken. NASA, to its credit, is not treating Artemis 2 as an endpoint. It's not treating Artemis 3 as an endpoint. It is treating it as a gate that must be passed before any additional complexity is added to the list. The presence of the rocket on the pad and the discussion of lunar power systems show a program moving from what we would call demonstration models toward operational planning. The emphasis is not on spectacle, but on verifying, well, the real conditions we're ready for. And that is why I believe this phase is way more important than even some are giving it credit for. But beyond low Earth orbit yes, it's great. But let's face it, low Earth orbit itself is undergoing a rapid transformation. What was once a relatively sparse operating environment is now becoming densely populated, driven for better or worse by large satellite constellations designed to provide global communications and data services. This growth is forcing governments, scientists, and space operators to confront the practical limits of what is quote unquote orbital space. And it's only going to get worse because one of the largest planned expansions is coming from Blue Origins, which has announced plans to deploy a satellite constellation numbering more than 5,400 spacecraft. The system is intended to provide broadband connectivity and compete with other large commercial networks that are already in low Earth orbit. And at the same time, researchers are documenting the impact of these constellations on scientific observation. Finally, a story that doesn't piss all over SpaceX. A recent study in examining Amazon's internet beaming satellites found that the spacecraft are bright enough to interfere with astronomical research even when the mitigation strategies are applied. Astronomers reported that reflections from satellite surfaces can contaminate images taken by ground-based telescopes, particularly during the twilight hours. Now, this concern is not tied to necessarily any single satellite, but to the cumulative brightness as thousands of spacecraft are now passing through observation fields. As the number of active satellites increase, so will their complexity of operating in orbit safely. Each of these spacecraft have to be tracked. They have to be maneuvered and coordinated with others to avoid collisions. The smallest positioning error or delayed data can increase the risk of not just close approaches, but of collisions. And with the ever increasing congestion, it also increases the long term debris problem. Satellites eventually fail or reach the end of their service life. Upper stages from launches can remain in orbit for years unless you're China and you can't get there anymore. That story's coming later. Fragments from past collisions persist, which also raises the likelihood of additional impacts over time. Now, unfortunately, Al Space Junk Removal did not win this next reward, but just to push Al a little further, the United States Space Force, through its Space Development Agency, has awarded a roughly $52 million contract to Starfish Space to actively deorbit satellites. Under the contract, Starfish Space will use its Otter spacecraft to rendezvous with satellites in low Earth orbit and guide them into a controlled re-entry at their operational end of life. The system is designed to work even with satellites that were not originally built with any specialized docking hardware. This represents a shift in how orbital debris is going to be managed. Historically, debris mitigation focused on designing satellites to passively decay from orbit after retirement. Active removal acknowledges that the current orbit environment is crowded enough to require intervention rather than reliance on natural decay alone. Tracking what comes back down, thankfully, is also improving. Researchers have demonstrated that earthquake sensors on Earth can detect the impact of space debris re-entering the atmosphere and striking the ground or ocean. These sensors provide independent data that can be used to refine re-entry models and better understand where any of the debris lands. Together, these developments reflect a broader change in how orbit is going to be treated. We have to remember that low Earth orbit cannot be viewed solely as a transit region anymore. It is increasingly treated as a shared infrastructure that supports communication, navigation, Earth observation, and security systems. Now, while social media oversizes the satellites in space and makes it look, oh my God, it's crowded, we do have to acknowledge that the infrastructure actually does have some limits. The benefits of satellite constellations are real, especially in an expanded global connectivity issue. But at the same time, the pace of deployment has exceeded the regulatory frameworks originally designed to manage some of this shared orbital space. And as more of these satellites are launched, coordination will become more critical, avoiding collisions, preserving access for scientific research, and preventing possible cascading debris events all depend on the sharing of data and operational discipline among multiple actors. But this current trajectory makes one point clear. Orbit is finite. Managing congestion, mitigating debris, and balancing commercial activity with scientific and operational needs will determine God, I hate this word, but it's accurate here. How sustainable human activity in space becomes in the years ahead. Well, that said, we do have Ars Technica putting out their weekly rocket report, and we thought there was some interesting information to use for tonight's show. Because guess who's back in the news?
And now, Assholes in Space!
China is asshole! China is asshole! China is asshole! China is asshole!
Yes. 2, not 1, 2 Chinese rockets failed within a span of roughly 12 hours. They were separate launches on different missions, but both ended unsuccessfully. Launch failures happen in every space program, and on their own, they're not necessarily unusual. What makes this notable is the timing and the broader context of when and which they occurred. Yes, China's launch cadence has increased significantly in recent years. More launches means more satellites, tighter orbital spacing, and less tolerance for error, which we know the Chinese are not great at. So when failures happen in that environment, the consequences extend beyond a single mission. Now, according to available reporting, debris from the failed launches fell into designated quote-unquote downrange areas, quote-unquote, primarily over ocean zones. There were no confirmed reports of damage to populated areas, infrastructure, or livestock. So for now, for the record, no cows were harmed, so we have to keep the same cow counter. Calling bull crap on the reporting, though, so we may have to just assign a random number to add because you know at least one was hurt. But yeah, separately, a Chinese crewed capsule recently returned to Earth after sustaining damage as well from space debris that was struck while in orbit. The spacecraft remained functional and the crew did land safely. And this incident highlights the growing hazard posed by debris in crowded orbital regions. So China was not having a good week. But let's not forget who is responsible for some of this space debris, shall we? Because China has previously conducted anti-satellite tests that generated long-lived debris. These fragments remain in orbit, contributing to the same environment, now threatening active spacecraft. And once debris is created, it does not belong to any one nation. It becomes everybody's problem. And concerns have also been raised about China's satellite behavior in orbit. A recent Popular Mechanics report detailed Chinese satellites performing close approach and rendezvous maneuvers. These operations resemble on-orbit inspection or interference testing, depending on how you wish to interpret. Now, China describes these activities as quote-unquote experimental. Other space agencies describe them as ambiguous at best, threatening at worst. In a crowded orbital environment, ambiguity increases risk. Close proximity maneuvers require some really good coordination and transparency to avoid collisions or forced evasive actions by other operators. Spaceflight only works as a shared system when participants accept shared responsibility. And right now, that responsibility, if I dare say so, is not being carried evenly. And let's not forget, the orbit keeps the receipts.
Doesn't take it opens like a field without edges. Move because there's a direction, not because it's the only one. Light leans into distance before it learns a name. Moments fall sideways, and still I ride the same. Every second has a shadow cast from somewhere else. I feel death in the passing, like a weight I cannot Time doesn't point forward, it spreads thin and wide. We travel one narrow bearing and call the rest behind. The future breathes beside us, close enough to feel a crossing we were never built to touch or turn or steal. There are directions without motion. There are paths without speed. What we call beginning is just where we agreed to enter the surface of something too wide to hold. We move along the edge of it because it's all
And welcome back. Sorry about that. We just had a little bit of a hiccup, so I'm going to end that intermission music a little early. And I'm not going to say I'm going to speed run this second half of the show, but if you lose me, understand Mother Nature won. So if the first half of the show was about systems we build and choices we make, the second half is going to be something else. Because while we argue about budgets, launch schedules, and orbital rules, the rest of the solar system keeps doing what it has always done. The sun doesn't wait. Planets, they tend not to ask for permission, and physics doesn't give a rat's ass whether we're ready or not. So while human activity in space is becoming more deliberate and more crowded, the rest of the solar system is doing what it's always done. It's moving energy around. Recently, Earth was hit by the strongest solar radiation storm in more than 20 years. According to space weather monitors, the storm originates from a powerful burst of activity on the sun, sending high-energy particles toward Earth at levels not since seen the early 2000s. The storm did not cause widespread damage on the ground. Power grids relatively remained stable, satellites continued operating, and aviation systems adjusted as they were designed to do. But the intensity of the event was enough to raise concern among space agencies and satellite operators. Solar radiation storms matter because, well, let's face it, they expose a growing vulnerability. Modern civilization depends heavily on space-based infrastructure. Satellite supports navigation, communications, weather forecasting, and timing systems that operate continuously. Strong solar storms can disrupt satellite electronics, degrade solar panels, interfere with radio communications, and increase radiation exposure for astronauts. As human presence in space is expanding, so does the exposure of the events. The sun does not produce storms on a schedule that aligns with launch windows or mission planning. It follows its own cycles, rising and falling in activity over roughly 11-year periods. The current solar cycle is approaching the more active phase, increasing the likelihood of additional high-energy events in the coming years. And Earth is not the only planet feeling these forces. New research suggests that Mars may play a measurable role. I hope you're sitting down for this. Please, okay. Mars may play a measurable role in influencing Earth's climate. I know 1,000 purple-haired freaks just heads bursted with that comment. Despite its distance and relatively small size, scientists have identified long-term correlations between Mars' orbital dynamics and subtle variations in Earth's climate patterns, particularly over geological timescales. Now, the effect is not immediate and it's not dramatic. Mars is not driving, day-to-day weather. Instead, its gravitational influence appears to contribute to slow changes in Earth's orbital behavior, which in turn affects how solar energy is distributed across the planet over thousands to millions of years. This kind of interaction reminds researchers that planetary systems are interconnected in ways that are easy to overlook when focusing on individual worlds, and modern climate change scientists are absolute frauds. Now, Mars itself continues to reveal evidence of a very different past. Recent observations strengthen the case that Mars once hosted a vast ocean, covering a significant portion of its northern hemisphere. Geological features and mineral deposits suggest the liquid water was stable on the surface for extended periods, long enough to shape coastlines and sedimentary layers. But no, the humans on Mars must have fucked that up too. Anyway, the ancient oceans are now gone. Whatever processes stripped Mars, sure as hell wasn't humankind, of its thicker atmosphere and warmer conditions, left behind a colder, drier planet. The transformation did not happen quickly. It unfolded over immense spans of time, driven by changes in atmospheric loss, magnetic field decay, and solar interaction. Really? Nothing of humans messing up Mars? Huh? Well, surely. Anyway, these processes are still being studied because they offer a natural experiment in planetary evolution. Mars shows what can happen when a planet loses its ability to shield itself from solar radiation. Without a strong magnetic field, the solar wind can slowly erode an atmosphere, changing climate and surface conditions irreversibly. Huh, huh. Farther out, similar forces are shaping the giant planets as well, where humans also exist. Scientists studying Jupiter and Saturn have identified unusual polar weather patterns that may provide insight into the internal structure of both worlds. Persistent cyclones and complex atmospheric motions near their poles suggest deep seated energy flows extending far beyond the visible cloud layers. These patterns are not seasonal storms, they appear to be stable features driven by heat rising from the planet's interiors, interacting with rapid rotation and powerful magnetic fields. Surely it's the humans' fault. Now, understanding those dynamics help researchers refine models of how large planets move heat and energy, processes that influence not just weather, but magnetic behavior and radiation environments that for some reason we don't apply to Earth. Taken together, these stories point to the same conclusion that solar system is not static. Except for Earth, where humans are fucking it up apparently. Now, energy flows outward from the sun, interacts with planetary atmosphere, shapes climate, and drives long-term change. Those forces do not pause because humans are busy building infrastructures or managing orbits. As we extend our presence beyond Earth, we are entering an environment defined by variability, radiation, and deep time. The systems we build must function within that reality, of course. And this is where the second half of the episode really was going to begin. As I take a deep breath, or breath, let me breathe, Jeff. Anyway, Mars does look dead now, cold, dry, dust scoured, a planet defined by what it no longer has. But new evidence continues to tighten the case that it wasn't always this way. It did, in fact, Mars had that large, long-lived ocean. Scientists have identified formations that resemble coastlines, deltas, and layered sediments consistent with prolonged interaction between water and rock. These are not signs of brief flooding events, they suggest persistence, because time is not something invented by the Swiss. And yes, we did learn the importance of breathing. For those that know, will get these jokes. Now, Mars is smaller than Earth, and that size difference does matter. Despite what anyone else tells you, size does matter. Over time, the planet's internal heat dissipated. As the magnetic field weakened without a strong magnetic shield, the solar wind began stripping away atmosphere molecule by molecule. As the atmosphere thinned, much like my hair, surface pressure dropped, temperatures fell, water either froze underground or escaped into space. This was not a sudden collapse, it was more of a long retreat, also like my hairline. Understanding that process is a priority for planetary science because it represents a natural experiment, a planet that crossed from potentially habitable to hostile. Mars, it didn't explode. It didn't suffer, as far as we know, a single catastrophic event. It just slowly lost its ability to protect itself. Now that matters because Mars is often treated as Earth's closest analog. Not because it is similar now, but because it may have once followed a parallel path before diverging. And humans, wiped everything off of Mars because of climate change man-made. Oh, wait, hold on a minute. Being told humankind may not have ever been to Mars. So, Anyway, the evidence for ancient oceans strengthens the idea that Mars was not just briefly wet, but habitable for extended periods. Whether life ever arose there remains an open question, but if it did, we know who to blame. But the environmental conditions appear to have been present. And that question will be an ongoing question for future missions. Orbiters continue to map subsurface structures. Rovers are analyzing mineral chemistry for signs of any water interaction. And sample return missions aim to bring Martian material back to Earth for detailed study. Each step will narrow this uncertainty. Mars, well, it also serves as a reference point for how scientists evaluate other worlds, except for Earth, where these seem to be blinders on. When astronomers search for signs of life on distant exoplanets, they look for atmospheric signatures that suggest stability, gases that should not coexist unless something is replenishing them. Mars shows how those signatures can disappear when planetary systems lose that balance. A planet can cross a line from habitable to barren without really any dramatic warning or signs. And in a way, this is why Mars isn't just a destination, it's actually kind of a case study. It tells us the habitability is not a permanent state. It is a condition that depends on shielding, energy balance, and that ever important piece of information, time. Mars had water, Mars likely had an ocean, Mars lost it. And understanding how that happened helps scientists refine models of planetary evolution, not just even in our solar system, but across the universe and the galaxy. Now, when astronomers talk about finding life beyond Earth, they are not talking about photographs per se. They're more talking about chemistry. Specifically, they are talking about the atmospheres. Because for planets orbiting distant stars, atmospheres are often the only accessible evidence we currently have the ability to see. We really can't sample the surface of, say, let me pick a random planet, something in the Alpha Centauri system. We can't drill into the rock. We can't send probes. What we can do is watch how starlight changes as it passes through a planet's atmosphere. That technique is known as spectroscopy, and it allows scientists to identify the chemical fingerprints of gases surrounding these distant worlds. Different molecules absorb light at specific wavelengths. By measuring which wavelengths are missing from a star's light during its transit, astronomers can actually infer what gases are present. And this is how scientists are planning to search for signs of life. Not by looking necessarily for organisms directly, though that would be absolutely amazing, but by looking for atmospheric imbalances. Let's take another random planet. Oh, I don't know, Earth. Where oxygen is a good example. Oxygen is highly reactive. Left alone, it should combine with other elements and disappear. The reason it persists in large quantities in Earth's atmosphere is because it is constantly replenished by this magical thing called life. The same logic applies to other gases such as methane. Methane can be produced by geological processes, yes, but when methane appears alongside oxygen in large amounts, it becomes difficult to explain without some ongoing source. These combinations are known as biosignatures. They're not proof of life, but they are indicators that something unusual may be happening. Modern observatories are now capable of searching for these signals. The James Webb Space Telescope is already analyzing the atmospheres of exoplanets, particularly the large gas giants and hot, close-in worlds where atmospheric signals are, well, let's face it, easier to detect. Future ground-based observatories, such as the extremely large telescope currently under construction, are expected to expand this capability to smaller, more Earth-like planets. But the challenge, well, let's not lie here, the challenge is immense. Atmospheric signals are faint, stars are very, very bright, except the Hollywood kind. Instruments sensitive must be fine-tuned because their sensitivity, they're going to have to be extreme, and planetary environments are going to be complex. A gas that looks biological on one planet might be geological on another. And Mars actually provides a cautionary example. Methane has been detected in trace amounts in the Martian atmosphere. On Earth, methane is often associated with biological activity. On Mars, Right now, the source remains unclear. It could be geological, it could be chemical, or it could be by a bunch of Martian cows living underground. But that's uncertainty is why astronomers have to remain cautious. Detecting a biosignature is not the same as detecting life. It is the beginning of a tedious process of elimination. Planetary context matters. A planet's mass, temperature, radiation environment, and geological activity all influence what gases can exist and how long they persist. There's, as far as we know, there's not a single gas that will confirm life. Scientists look for the patterns, the ratios, the stability over time, inconsistencies that resist the non biological explanation. And the crazy part is, even then, conclusions will not be definitive. Now, the ultimate goal should be to not announce discovery prematurely, but to build the confidence step by step, case by case. This work also forces scientists to refine eventually how they define life. And for the love of God, can we start exploring how we define what life is? We can't even do it with Earth life. How the hell are we going to do it with other planetary life? By almost every measure, modern physics works. We can predict planetary motion with amazing accuracy. We can model stellar evolution, simulate black hole mergers, and even detect gravitational waves from across the universe. But yet, one variable continues to resist clean explanation. Time. More than a century ago, Albert Einstein, showed that time is not absolute. In his theory of relativity, time stretches and slows depending on speed and gravity. Clocks on satellites tick differently than clocks on Earth because the ones on Earth were made by the Swiss. And time passes at different rates near massive objects. That part has been confirmed experimentally. What remains unsolved is how time behaves at the smallest of scales. For in quantum mechanics, time is treated differently. It is not flexible, it's not dynamic. It is assumed to flow uniformly in the background while particles and fields evolve within it. Now, this assumption works until quantum mechanics is compared directly with general relativity. The two frameworks describe relativity extremely well in their own domains, but they do not fully agree with each other, much like my second wife and I at divorce proceedings. Time sits at the center of that disagreement. The quantum stuff, not my ex-wife, that was more monetary. Anyway, one recent theoretical proposal suggests that time may have more than one dimension. In this framework, what humans experience as a single forward moving timeline could be the result of motion through a higher dimensional time structure. This idea is mathematical, not experimental. There is no evidence that time actually has multiple dimensions. Oh, it would explain a hell of a lot. But the proposal exists because it allows equations to behave more consistently across scales where existing models are struggling. Another area of theoretical works involves cosmic strings, hypothetical defects in space-time that may have formed shortly after the Big Bang. These objects have not been observed, but some cosmological models do allow for them. If they exist, cosmic strings would be extremely dense and would distort space-time around them. Under very specific mathematical conditions, those distortions could allow paths that loop back on themselves in time. Meaning, yes, time travel would be possible. It means that the equations describing space-time permit unusual solutions, even if the universe never realizes them physically. I mean, this is how theoretical physics works, for those that do not know. Physicists explore what the math allows, then look for evidence that nature actually uses those possibilities. What we don't like to admit, most proposed ideas fail that test. Very, very few survive. At present, neither multidimensional time nor cosmic string time effects have experimental support. They are just tools for identifying where current theories break down, not predictions of future technology. What they actually highlight is a deeper issue. Physics can describe how time behaves under many conditions, but it still cannot fully explain why time has a direction at all. Entropy increases. Systems move from order to disorder, but why that process aligns with a single forward arrow remains a bit of an open question. Even after a century of refinement since Einstein and drink, time remains the least understood part of physical framework. We can measure it precisely. We can manipulate it indirectly. Yet we cannot fully define it. As we push further into space, away from Earth, away from familiar conditions, these unanswered questions will matter more, not less. We're not attempting to resolve time. It really is, it marks the boundary of what we currently understand. It reminds us that even with better instruments and better data, some parts of reality are just incomplete. But we shouldn't look at this as a failure. We should look at it as a frontier to fully explore, as long as we're not reclining in our lounge chair commanding a ship. And as we move now through the final days of January and into early February, the winter sky is remaining stable, if not in a complete and bitchy mood. We are, in the middle of an important little part of the year. Let's start with the sky itself. If you can see it from the 3 segments of Florida that probably don't have snow in it. After sunset, Orion is already well placed in the south, marked clearly by the 3 stars of his belt. Below him, Sirius rises in Canis Major, low and bright, often flashing with color as the atmosphere bends its light. Above Orion, Taurus holds steady with Aldebaran glowing orange, and the Pleiades cluster remaining visible as a small, tight group, even to the naked eye. Jupiter continues to dominate the evening sky, bright and steady. Binoculars will show its most likely 4 largest moons changing position night to night. Mars is also visible, slightly dimmer and distinctly reddish, sitting further from the sun now, but still easy to pick out against the background stars. But now we get to the main portion of this, the moon. This 2-week window includes a full moon. The moon will reach its full phase around February 1st, washing out fainter stars for several nights on either side. During that stretch, deep sky observing becomes very difficult, but lunar observing works just fine, especially with binoculars, where surface details along the edges remain interesting even at its fullest phase. Now, in many indigenous traditions, the moon is also known by names tied to late winter conditions. Among the Ojibwa, one traditional name for the February moon is Makana Gazas, roughly translated as bear moon, referring to the time when bears begin to stir near the end of winter. As always, names vary by nation and region, but the intent is the same, marking a practical season moment, not celebrating a spectacle, and laughing at Jeff as he tries to pronounce any of them. I can speak Finnish, but I can't speak any. I don't get it. Anyway, as the moon wanes after February 1st, darker evening skies return quickly. By the first week of February, conditions improve again for star clusters, Orion's nebula, and faint background detail if you're away from city lights. Early mornings will remain quiet and clear. The eastern sky opens first, and winter constellations slowly begin their westward tilt, making room for what comes next as the season begins to turn. Cold air, when it cooperates, still offers some of the best seeing of the year. Stars sharpen twinkling softens, and even modest equipment performs best. Remember, the sky isn't changing fast right now. It's holding steady, and that makes this a good window to simply look up, take your time, and let the patterns settle in. That's it for tonight's transmission. Thank you for tuning in whenever and however you do. Special thanks to NASA, SpaceX, Spaceflight.com, Ars Technica, NASA, Spaceflight, Popular Mechanics, and everyone out there keeping humanity's eyes on the star. With me at the helm, the executive producer plotting our next course, and the ship's computer in the back whispering star maps through the static, this has been the Lost Wanderer podcast. Until next orbit, I hope you enjoyed the show, learned a little bit, and maybe had a laugh or two as well.
The universe is a pretty big place. It's bigger than anything anyone has ever dreamed of before. So if it's just us, it seems like an awful waste of space. Right?
When I was young, it seemed that life